So our goal with this question is to find the power that is being delivered by the voltage source here. So to use the mesh current method, I need to label my meshes. So I'm going to write here IA, IB, and I will also have a mesh up the top, which I'm going to call IC. So then my process is to apply KVL to each of these. So KVL at the mesh labeled as A will give me the following equation. So starting at the bottom, I will have minus 80 volts. The voltage across the 5 ohm resistor will be current contribution due to IA minus contribution due to IC. I can see that those currents will be in opposite direction if you kind of visualize it from the perspective of this resistor. So they're flowing in the opposite direction, and therefore I use the minus sign there. Proceeding further around, I have the 26 ohm resistor, so it will be plus 26, and I will have IA and then minus IB. Again, I can see that the arrows are pointing in a different direction, and all of that is equal to 0. So just simplifying this expression a little bit, I will have IA, I should collect like terms on that, so like terms will give me 26, so 31 times IA. I will have minus 26 IB minus 5 times IC is equal to 80. And that is equation number 1. Looking at mesh number B, if I do Kirchhoff's voltage law at mesh B, then here is what I will get. So I'll start at the bottom and look at that 26 ohm resistor first. So 26 ohm resistor, IB minus IA, because IA is flowing in the opposite direction. The next one will be the 90 ohm resistor, so 90 times IB, and looking at the arrows, that will be minus IC. IC will be the opposite direction than IB at that point in the circuit. Finally, 8 times IB is equal to 0. We can simplify this expression a little bit. So I will have minus 26 times IA. My IBs will give me, I'm just going to quickly calculate, so that's a 26 plus a 90 and an 8 will give me 124 times IB, and then minus 90 IC, and that is equal to 0. And that will be equation number 2. Then I need to do Kirchhoff's voltage law at the mesh C. And for this one, I'll choose a starting point, let's say like that top left corner there. So proceeding around in a clockwise direction, I will have 30 times IC plus 90 times, I will have here IC minus IB, then the 5 ohm resistor, IC minus IA, and then I'm back to where I started, so that is all equal to 0. We can simplify this equation a little bit, so I'll just write them in order. So I will have minus 5 times IA, Then my IB terms, there's only one of them, so that's a minus 90 times IB. And then my IC terms, I'm just going to quickly calculate those. So that's 30 plus 90 plus 5 is 125. IC is equal to 0. And that is my equation number 3. So I now have 3 equations, 3 unknowns, but let's be a little bit strategic about this. I actually don't need to solve all of them. If my task is simply to find the power delivered by the 80 volt source, it would be sufficient to solve for mesh current IA. if I know the voltage and the current at that source, I can calculate the power. So in particular, what I need to do at this point is just solve for IA. Solve for IA. When I only need one answer out of a 3x3 system, Kramer's method is a good approach. So let's go ahead and formulate this as a matrix. So I will say I will use Kramer's method. So writing this system as a matrix, here is what I will get. So equation 1 is that 31 IA minus 26 IB minus 5 IC. So IA, IB, and IC is equal to 80. Second equation is a minus 26, a plus 124, and a minus 90 is equal to 0. And my third equation is a minus 5, a minus 90, and a 125, and that is also equal to 0. So to use Kramer's method, I need to know the determinant of my A matrix. So determinant of my A matrix being this one here, will be as follows. So I have 31 times the determinant of kind of the other portion. So take this top left element and then look at the matrix that's made up with the other rows and the other columns. So that will be determinant of 124 minus 90 minus 90 and 125. That is subtracted by the determinant of this element with a matrix that's made up of the other pieces. So let's quickly have a look at that. So that will be minus 26 times the determinant, negative 26, negative 90, negative 5, and 125. Finally, alternating signs will give me minus 5. I'll just clean up my highlights and we can analyze the final part. So that's a minus 5 with determinant formed by these other pieces here. So minus 5, determinant of negative 26, 124 minus 5 minus 90. Let's go ahead and calculate those. So that is 31 times, and this is just the diagonal product. You can pretty much just type it straight into your calculator. So 124 times 125 minus 90 times 90. So that will be 7,400. The next one here will be plus 26 times, again, I can pretty much just type out this determinant, so it's the diagonal product. So it's negative 26 times 125 minus the other diagonal product. So the other diagonal product is just going to be 90 times a 5. So this is negative 3,700. Finally, I will have minus 5 times, again, I can pretty much just type this out, negative 26 times negative 90 minus 124 times a negative 5, and that will be 2,960. Evaluating all of this now. Bear with me. 26 times negative 3,700 minus 5 times 2,960. 118,400. Now for IA, I need to know the determinant of this N1 matrix, which will be the determinant that I get when I replace the right-hand side. So the right-hand side being this B vector over here, replace that in the first column. So I will have 80, 0, 0, and then I just read off the rest of my matrix. So the rest of my matrix is negative 26, 124 minus 90, a minus 5, a minus 90, and a 125. And I need to go and calculate the determinant of this. So determinant of this matrix is going to be 80 times the determinant of 124 minus 90 minus 90, 125, minus negative 26 times the determinant of what I get with the other columns and the other rows, which is that. That matrix is nice because it will have a determinant of 0. You can see from both diagonal products are going to multiply out to 0. And then finally, plus the remaining terms, so there was a minus 5 times the determinant. And again, I'm going to get something that's a little bit nice because I will have zeros there. And you can clearly see that determinant will also evaluate to 0. So without really doing any further work, I can clearly see that these terms here will be equal to 0. So I really only need to evaluate this first term. In fact, it's the one, or this determinant here, I in fact have already calculated. So you see it's the same here, and I calculated it to be 7,400. So I can actually just write that number straight down. So this will be 80 times 7,400, which is 592,000. So this therefore tells me that my current IA is determinant of M1 divided by determinant of A. So that was 592,000 divided by determinant of A, is just this number here, which is 118,400. And that one is 592,000 divided by 118,400 is 5. So IA is 5, so 5 amps. And I can now go back and look at my circuit, and I now have a situation where I know the voltage and I know the current, and therefore I can calculate the power. So in particular, I will just redraw this just for clarity. So the power at the source is going to look like this. So I have voltage source. It was a 80 volt source. It's an 80 volt source, and I know that there's a current of 5 amps flowing through it. And so the power here, power enters the negative terminal, the current enters the negative terminal, so it's going to be negative 80 times 5. If you weren't sure about the negative, you could also look at this. I mean, you can just see it's obvious. This is the only place that power can possibly be injected into the circuit, so obviously it has to be negative by the passive sign convention. There's nothing else here that can possibly be acting as a source. So you could also make the argument just intuitively based on the passive sign convention. So negative 80 times 5, 5 8's 40, so this is minus 400 watts. So we have power here is 400 watts, therefore 400 watts is delivered. So I hope that one is another useful example of how to apply the mesh current method. Essentially, to summarize this one more time, for each of our meshes, we would write down what is a current through that mesh, IA, IB, IC, and we use KVL around each of the meshes to generate our system of 3 equations, and then we solve those equations to get to our final answer.